Yeah. All right. Music is up. Link is in the chat. Mumbai Cakes on time as per usual. Okay. How are you going, dude? Ready to just chill for a little bit while we wait? Maybe just a second.
Sure.
Sure. I think I sent you a message. Do you have any thoughts on Rising Earth lined up for me?
Rising Earth?
Yeah.
So did I miss something?
Yes, the Earth is rising. It's just going up and up and up and up and up forever.
Oh, you mean, that wasn't that, didn't someone propose that sometime ago, whatever?
Look, I've heard it a few times now. It's majority. I'm gonna make sure I don't stuff up my little mic.
It's still working.
Good. I know. If I move, it might break. That's the thing that worries me. Maybe I might turn it sideways. If I turn it sideways, then the thing does not hang.
And he's gone. He's gone again. We live? There we go. He comes back again. He goes out, comes in.
God. God.
Get yourself a pair of Rig. Was that 800 Pro HD Rig headphones? Man, they're pretty good.
You'll have to send me a picture of it in the private chat or something like that. Look, I mean, I got a Blue Yeti. It's a good one, but the problem with it is obviously that my kid has spun around the wheel in the seat so many times that he's knocked the microphone to the floor.
Well, this the microphone's on my headphones, not anywhere else.
Yeah, well, my one's one of the professional ones that sit in front of your face.
Oh, I see. All right.
Yeah, it's up on. It's really fucking heavy, actually. It probably weighs about like 3 kilos. I don't know how heavy it is. I should weigh it one day, but it's pretty heavy.
Yeah.
Okay, so let's. I'll turn off the music. Yeah, we're live. All right. Yeah, we've been rolling for about 2 minutes now. Okay, I'll turn off the music.
Mm-hmm.
One thing I haven't checked out is can I share myself doing MS Paint or something like that? That's what I'm kind of curious about. Do you happen to know if there's any browser pages where you can draw on at all?
Well, you've got Paint on your computer, don't you?
Yeah, I know, but this sharing program, sometimes I guess it wants to share the entire screen.
Yeah.
Oh, okay. Here we go. Window. MS Paint. Let's see.
At least we're reasonably good at tech on this side of the world.
What is going on here? Okay, so add to stage.
There you go.
A fresh sheet of paint.
Of dirt. Go
on. Okay, so essentially here, I just want to write.
The world goes up at an infinite speed. Oh, yeah, okay, that's a good one.
Okay. I'll make that capital. I was obviously an uppercase there. Okay, so you see that?
Lefts are wrong. And they are wrong.
Thanks for tuning in, everyone. Our episode is over tonight. That's all done. It's all on capitals.
They're so bad.
Is stupid.
Stupid. Yes,
there we go.
Definitely.
There we go.
So
there's more evidence to prove that that Rising Earth is stupid.
Yeah.
It doesn't make much sense. No, have you come across anything with Rising Earth recently at all?
Not recently, no. But I did hear I think 2 or 3 people propose it, but they were quickly knocked down because if the Earth is rising, because they're trying to get rid of the gravity, right? Because I think
here we go. What I'll do is what I'll do before you start talking, I'm going to select this. I'm going to clear it. Now, okay. So it looks like everything inside this inner zone is okay. So I'm just going to create a box.
Okay.
And so I'm going to try to draw within this box because hopefully that should stay within the viewport.
It's in a container. Ooh.
It's in a container. Okay. Now, if you want to throw some things at me, you tell me what you were just about to say, and I'll write them down as thoughts.
Thoughts.
Yeah, thoughts. Yes.
Okay, so
Okay.
The Earth is supposedly their argument is the Earth is rising at whatever speed it is, 1,000. The same speed that the gravity falls at, which is
wait. So you're saying Earth rising at 1,000 mile per hour?
No, the same rate as gravity falls, like 98 point whatever it is second squared or whatever it is, right?
I got to avoid doing small e's. Yes. So yes, 9.8 meters per second.
Second squared is what the Earth is supposed to be rising up to.
Can I make the 2 smaller? I don't know. Let's make it a 2, but let's make it a lower one. Yeah, I'll make it a bit bigger. We can use this again and again. Is crypto roast in the thing? Oh my god, Roofy's in the thing. Let me just check the comments. Okay, Cakes, you spelled piss wrong. Did you write piss? Did you?
Did I?
I don't know. Okay,
so our hero.
Well, look at this. See, this is a bit like was it not SpongeBob? You know the green guy on Monsters Inc.
Yeah,
the one-eyed guy, right?
Mike Wazowski.
So he's always in the images, but he's always blocked out. And as you can see, Crypto Roast is currently blocking out Roofy.
There we go. Nice, Mike Wazowski.
Yeah, Mike Wazowski. That's his name.
Yeah.
So, so 9.8 meters per second. I agree, and that is the reason why it is squared is because that's acceleration. Correct?
Yes.
Okay, so
I'm so glad we got Roofy in the room. He's much smarter than both of us combined.
Well, I consider myself pretty smart, but we have our parts which where we're best at.
Yes,
I like
everyone's good at something,
and Roofy obviously likes to do refraction calculations where I don't do that sort of stuff. So yeah. Yes, so the important thing is it's 9.8 meters per second acceleration. Do you have any idea what the speed is for someone who's skydiving?
No.
150 k's an hour, isn't it? Something like that.
Might be. I don't know. At one point in time, I did do a video a while ago. So what was 150 kph?
Yeah, which is about 40 meters per second, something like that.
40, yeah. I would probably agree because
42.
Because I did a video a while ago where I was talking about it, and I calculated that the acceleration was you'll probably hit terminal velocity at around about 3.5, 4 seconds, maybe even slightly pushing towards 5 seconds.
Yep.
But they say that it's much closer to 5 seconds for terminal velocity. So I got terminal velocity.
Yes, and when you hit the ground, you're terminal.
Yes.
Well, that's the thing. I mean, okay. That's one term. That's one term for terminal.
That's why you go to the airport if it's terminal.
Cakes, what do you believe the terminal velocity is?
Pass.
Pass? Okay.
I have
Roof?
no idea.
I'm sure.
What do I think the terminal velocity is? Didn't we just say it's 150 k's?
Yeah. I'm not talking about numbers. I'm talking about what it actually is as a theory.
Oh yeah. So the force of the air resistance stops you from accelerating any further.
Yeah.
Yes. And I would agree. I would say that the terminal velocity varies upon altitude. So if you're closest to the ground, the terminal velocity would be lower because the amount of air particles around you is slowing you down. Whereas, let's say, for instance, our good old Red Bull guy with his extremely curved cameras, he was obviously spinning completely out of control because his terminal velocity would have been very, very high, and the wind resistance on his knees and on his arms could not steer him enough to be able to get out of a good spin until he hit more air.
He reached Mach 1, didn't he?
Also, though, there's less
Yes.
gravity as well. So there's a
Yes.
Yeah.
Yes, it is variance. I think I might have wrote that down once. So at one point in time, so down on the ground, we're at 9.8 meters per second. I believe that at the Kármán line, I think it is 9.2 or 9.3 meters per second.
Cool.
And I think that at Mount Everest is about 9.57 or something like that. So it's kind of close. So this is I'm just going to assume approx gravity. We'll go Mount Everest. Oh God, yep, yeah, that's fine. We'll say it's about, let's say 9.6, and we'll say Kármán. Look, I'm going to say 9.3. I think. I don't know if anyone is okay and agreeing with the fact that I'm currently doing it like a bit of a learning mission. It's kind of like we almost need Professor Phil Bell to be in here to give us high school lessons to some degree. But I thought that I would just try to run over some of the theories about what rising Earth, how it conflicts with gravity. And okay, let's start with, what do you think would be the problems with rising Earth?
You would reach the speed of light quite quickly.
Yep. So Earth reaching.
But really, would you feel it though? Because
probably. I don't know. Yeah. Because we're already experiencing 9.8 acceleration already.
Yeah.
So this is the thing. So when you're in a rocket, and you are accelerating, when they lift off and they hit about like 100 kilometers or 200 kilometers per hour at the base in the first 50 or 100 meters, they reach new G level. They reaccustomize themselves to the new G level as they accelerate.
Right.
So I think it's an important point to write there. So rocket G's, you adjust. Do you think there's anything else that's wrong with rising Earth? I was thinking about one particular thing. If you had a flat Earth and if it was rising, apart from the fact that you would need infinite space above you to be able to move into, you would also, if it was flat and if you didn't have the container that is the thing, all of the air would flow off the side and out down below.
That's a good point.
There's a dome. There's a dome.
I know, that's the thing. If firmament, right? If firmament. No loss in air. If no firmament.
Would the gravity increase too? I mean, like so if you're increasing to light speed, wouldn't our bodies start to like shrink and get heavier and stuff like that?
No,
I don't know.
The acceleration's constant.
Okay. I don't think so. Yeah, I don't think so. I'll be curious if Andrew Johnson actually has any interesting comments on this one too.
Yeah, come in, Andrew. Be another.
Come in, Andrew. Come in, Crypto. It's all good.
Another face in the stream.
Man, I'm more than happy to dox myself to you, but not on stream. I don't think. What's he got? Crypto on Swallow. Don't forget, on Rising Earth, there is no reason why. Here we go. There is no reason why a mass would weigh differently at different latitudes. Same for all favors on Earth.
Yep.
Interesting. Okay. Yes. So, critical things. I'm going to need to start reducing the text size here. I'll bring it down to 20. Okay. Critical thinks
So,
experiment
So now I understand.
won't work.
When you said Mount Everest and the Kármán line are different accelerations.
Yes.
Isn't that a disproof of upwardly accelerating Earth? It'd be
Let me have a
9.8
think about it.
all the way.
Yes. 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 But see, this is the thing is every time I've been in chats and I've been asking, is it still 9.8 meters per second? Nobody replies. Nobody ever replies. So, but you've got a very, very interesting point. So differing gravity, right?
There's no R squared if in an upwardly accelerating.
You're gonna need R for that.
Gonna need yes.
Arr!
Yeah, I'm typing fast. Yeah. Differing gravity, incorrect acceleration. Did I write down? Oh, I don't think I did. I didn't think I wrote down. So if we were rising Earth, we would need eternal space.
Mhm.
Eternal
Infinite space.
space. You're right. You're right. Space to move into.
Space, the final frontier.
Okay, so one of the things that clicked with me today when I was thinking about this too is how we're always talking about we as globers always get attacked for saying how come the stars like Polaris and Orion and Alpha Centauri have never moved over centuries.
Right.
If we were rising, the stars would peel away. Would you agree?
If they're on the firmament, no. If they're part of the thing that's rising up, But then, the stars have to be a long way away because they don't parallax, or they don't.
Well, they haven't got a clue what parallax even means. I mean, even I just heard Flatzoid talking about parallax when he was just simply talking about things in front of him. Not understanding parallax technically is for stars. Star alignments.
But everything's in the dome, isn't it? Like just painted on there.
Well, that's it.
If the dome, stars. If the dome is some relatively short distance away in terms of the distance between two observers, then they necessarily would parallax, and we don't see that. So they've got to be far away.
No.
Okay, what about airplanes flying above the surface? What about butterflies flapping its wings?
Yeah, I think they're fine.
You think?
Yeah. They all experience an acceleration. So
yeah, they all experience an acceleration, and they would need to continue their forward trajectory to be able to make sure that that lift is ensured with the wings.
Okay. Yeah, I don't think that'd be different on a upwardly rising.
Okay. What about light?
Would the sun set quicker if it's if it's going down?
Well, we got to first ask what is the sun connected to?
Yeah.
It has to be part of the whole upwardly moving apparatus. Yeah.
Yeah.
Has to be.
Yeah.
Can we work out how long it takes to get to light speed?
How long it takes? Oh yeah, for sure. Do you have a calculator up? Or do you want me to fire up a calculator?
Yeah, great.
What is it?
Actually, it's probably going to be it's going to be far easier to do it in Excel, isn't it?
Divided by 9.8. It's going to take 30 million seconds.
30 million seconds.
Divided by how many seconds in a day? 86,400, something like that. Days, 353 days. So it takes a year to reach light speed.
Mm-hmm.
Yeah. In fact, let's ask ChatGPT. ChatGPT.
Okay, so we know for a fact that nothing exceeds light speed. So I'm in my 40s, right? And I'm sure most of you guys are probably somewhere between 30s, 40s, 50s, or something like that. I don't really know. But if if we hit light speed after 1 year, I'm just kind of curious. Is it 11 months or is it 12 months? Find out what ChatGPT says. That would mean that we have see. This is the thing. Can you get the formula and can you get it to ask what speed you have achieved once you reach 10 years? Because I mean, my kid's almost 10 years old. I mean, we've gone to maybe warp 9.7 in 10 years. I don't know. I don't even know. To tell you the truth, I don't even know what the factor of speed is for most of Star Trek's warps anyway.
Yeah, who knows?
But I know that they're exponential.
Warp factor 7.
Yeah, I think warp 2 is almost like 4 times faster than warp 1 or something like that.
I don't know. Sounds cool though.
It does sound cool. It does sound cool. Can we attach a couple of phases onto the landmass so we can shoot the Klingons on our way through? Oh, here we go. Professor Phil Bell. Now he is one guy who I really think really should be in this conversation. We could certainly do with his brain thinking. So his brainstorming from a teacher's perspective.
Yeah. Get in the chat, Phil.
Yeah, jump out of the chat, Phil, and get actually in live because we're talking about rising Earth, and let's talk about physics. Let's talk about actually what breaks.
Yeah. So I just asked ChatGPT for a relativistic answer.
Yes.
And it said the time required to reach 99% of the speed of light is 6.81 years.
Ooh.
6.81 years.
Yeah.
So does that mean that this original one is incorrect?
It ignores relativity.
It ignores relativity.
Yeah, so that's just a straight linear acceleration at 9.8.
Okay.
I see.
And Phil Bell can hopefully explain relativity like 1,000 times better than I could.
Okay, so 6 point how many years?
6.81 years to get to 99%.
Anything relative to me? My parents.
Now, I wouldn't mind. Like one thing I actually have sort of memorized is as far as I remember, it's 299,000 or 299 million meters per second.
Yep.
Roughly in that ballpark for light speed.
Is it per second? Or is it per second squared? Yeah.
No, it's not per second because it's not accelerating. Light speed is a known.
Is that the one way speed of light or the two-way speed of light?
Oh, come on, Jeff.
It's C. As far as I remember, light speed is C.
Yep.
That was the stupidest thing I've heard. What's the one way speed of light?
It takes 10 times longer to get to 99.99% of the speed of light.
Wow.
Really? Okay, but we're talking about we're not talking about real life. We're talking about this is almost like that that thing where you said, oh, would you rather like $100 or one cent doubled for the month? You know what I mean?
Yeah.
So we're not talking about exponential rises. We're talking about just simply double or whatever like that. But yeah, that's like, how does it go again? It goes 9.8, then it goes 19.6, and then it goes to like 12.4 or something like 26.4 or something.
Yeah. Oh, that's your linear acceleration.
Yes.
If Phil Bell comes in, he could explain the relativistic effect.
Yes.
All right.
But basically,
my invite's still up there, isn't it?
It should be. I clicked it. Stick it in the chat. Boom.
In the chat? Oh, yeah.
In the YouTube chat.
Okay. Well, the last one just still says hello.
Or maybe it got muted because I posted a link. Got to give me mods.
Okay.
Got to give me mods.
Okay, do you want to put it in private chat?
It's just a link to the. Actually, I'll do it to Phil Bell. One sec. Phil.
Or did you if you got a screenshot or something like that, I can share your screen or something.
No, I'll just message Phil. That's all right.
Okay.
Yeah.
You have backward. You have contact outside of this.
Oh, I've got a secret back channel to Phil Bell.
Yeah, right.
Ooh.
Yeah.
What else could there be? Because I mean, I've been pondering all this sort of stuff today, and there's so many things on this particular list which just seem so physically impossible, and they don't make much sense at all.
Yeah.
Okay, Bell is coming in.
He is. Hey.
Yeah, he's gonna come in. He's got to turn his computer on.
All right.
When he turns on, he probably has to press the turbo button. You remember the old turbo buttons?
Oh yeah, I had a 486 SX25.
Got to get it. He's got to pedal under the table to get it faster. Because you got to get that computer on.
Yeah.
What else could that be? I mean, the water would be okay, wouldn't it? I think the air might be okay, but yeah, it has to be trapped. And so when it comes to a firmament, we need solid glass. Now, one of the things that I was talking about with, I quizzed one of the concave earthers. I said, "Can you please remind me again what the distance is to the first layer of glass?" And he says, "I've already told you before. It's 100 kilometers." And I said, "Okay, so if it's only 100 kilometers, and if I look up from the sky, from just outside of Melbourne, I should be able to see a reflection of Melbourne above my head." Shouldn't I?
I think the easiest.
If I look up, I should be able to use the binoculars and kind of like try to figure out the streets of where Dano Road is and where half of the roads are in Melbourne. I know where the central the Yarra River is. If I looked at the reflection 100 kilometers up, it's visible at 100 kilometers.
Yeah, I think the easiest one though is like ask them. When the sun rises, how far away is that? All right, we know the GP of the sun, and it's like 6,000 something kilometers, 6,000 miles away.
Yes.
So the firmament has to be at least 6,000 miles up, or spherical radius, 6,000 miles. Feels.
Yes. Coming. Well, the thing is, if you've got a sunset coming up from the very, very bottom. And they've got a glass layer which is 100 kilometers high, and the glass layer is peeling away from you at an upward vector, then that piece of glass will never deflect a sunrise down to water level at any point in time ever. And I've often said that that when you if the layer of glass on the concave Earth ceiling is a similar thickness from the bottom to the top, as in if it's a standard 1 kilometer thick or something like that, and it's curving away at a nice even speed, then any light that would enter the area. Let me just
draw it.
Yeah. Okay. So let's say this. I'm gonna make it elliptical, right? So that it makes it a bit more like I've looked at it from a much closer zone. If the light is traveling, let's say I'll make the light yellow. If the light is traveling at this angle, and then it straightens up to be able to go through the glass, right?
Yeah.
In the end, it will exit at the exact same angle that it entered. So if this is like 30 up here, I'm going to have to boost up this text a bit. But if that's 30 up there, and let's say I don't know roughly numbers, but let's say it bounds through the glass layer at an angle of 35, then it would exit at 30, and you wouldn't go and get the bending effect that these guys want. Because I've seen pictures of the concave Earth, and what they try to say is that the sun is like in the center, right? And it ejects the light out like a big burning anus, lighting sun, like light everywhere, and all the way back around to where you are, like that.
Yep.
Which is weird.
Yeah. Right? So Walter Bislin's model. Right?
Sorry?
Walter Bislin's model basically what it does is stick the sun and all the stars in the ceiling, right? And then uses the globe for each observer, uses the globe to work out where you should see the sun and where you should see the stars. And do you know what a Bezier curve is?
No,
Like
fill me in.
It's if you give it the 2 points that you want the curve to go through, and you can give it a direction. So you basically construct the curve that you need to make the light come from wherever you want it to come from. Like that's all Walter Bislin did, is to just point the light wherever it needs to be. There's no mechanism to it.
Yes.
Yeah, but flat earthers like Shane and Alan,
they keep peddling it. Whenever I look at the Walter Bislin model, and I see the sun way over in a bent zone, the only way that you can attribute that is if you give it an artificial height, and if you put it over the GP. Because if you're a person down on the ground and you're seeing the sun setting in a particular direction, you can't simply say, well, it's set it there, so it's 90 degrees over on the right, because you can't see it. You can't see it that way. You only see it where it actually set. And so the only way that you can attribute the sun being all the way over to the right is to say, okay, I'm only going to review it according to its GP.
Yeah. Which is like at sunrise, sunset is 6,000 miles away. So, yeah, at least.
Yes. Welcome, Crypto Roast.
Yay.
How you going, Chief?
Hey, how's it going?
Not bad.
Lovely.
How's it going over in? How's it being a moderator on Jaron's channel?
Me or Crypto?
Oh, I'm guessing both of you guys are.
I'm admin. I'm admin.
He's admin in Jaron's chat. What about the YouTube chat?
I'm a moderator in the YouTube.
Oh
chat.
no, not YouTube.
I didn't get that last bit. Did you say something?
Yeah, Jaron's.
And you cut out again.
Sorry, I was just going to say
I think your mic is
Jaron's
coming in.
not happy about me being made a admin.
I bet.
Mine.
You know what? You know what I got this week? I got a spanner on McToon's channel.
Nice. He's got the shout out about the.
Oh, that's cool.
Fuck, what was it? The fuck. It's blown my mind. What was the?
I did the I had a video on the on
the turning around.
The boat. That got done by the HMS Hobart.
Yep.
And I was pissing myself laughing at that. That was hilarious. And I knew it was coming. I don't know if McToon doesn't deliberately not watches it prior to watching the thing so he can get a natural laugh.
Yeah.
But I knew it was coming, and I was ready for it. Yeah. That was fantastic. So yeah, I'm getting spanners. Who hasn't got a spanner here?
Me. I tried to post a link in the chat.
Oh, okay. Well,
spanner me.
How do I gotta remember how to do it. I think I have to watch my own video and then do it from YouTube.
Yeah.
Okay. Yes. Right, one comment. Yep.
FTFE gave me a spanner, but it kind of when FTFE gave me a spanner, it wasn't all that special because literally everyone gets a spanner in there.
Oh yeah.
No, I had to ask. I didn't get a spanner for a long time in FTFE.
Oh, add as moderator.
Oh man, it's a sea of spanners in FTFE's chat.
Well, I mean, there's so few amount of people who are watching me. Everyone will get a spanner. Here you go, Golden Skeptic. You get a spanner too.
You get a spanner. You get a spanner. Let's see if I can post the StreamYard.
Yes. Do that now.
Oh, there we go. Done. Boom.
Okay, Boomer. Okay, so let me get out of.
I'll vouch for OK Boomer.
Yes, we I think he came on. It was two streams ago. Here we go. Professor Phil is up. My God, I'm going to have to clear my my front page unless he wants me to draw something. And can you? Okay, I
Yeah,
think
I
I
mean-
think Professor's talking, but I can't do anything about it. Let me just see if I can copy
Unmute yourself
his-
there, Phil.
Hey, you muted, Phil. Down the bottom.
Hey, Phil.
That is not the correct link.
Check your settings, Phil.
What did I post? Oh, whoops! Hang on. That's
Yeah, I
the
think you just
YouTube
posted
link.
my own video, so I'm
Yeah,
going in
sorry.
loops.
Whoops. Doesn't matter. Doesn't matter.
There we go.
Oh, I'm
There we
getting
go.
more views by
Hey,
doing it for
Phil.
myself. G'day, Professor. How you going?
How you going?
Not bad.
Well,
Hey,
you
Phil.
guys, well, I was with my wife, just sitting down, on the bed watching a show, and then she goes to me, "You're off to talk to those silly flat earthers again, aren't you?"
You said no, right?
Except
no.
the thing is, none of us are flat earthers.
Oh, yeah, I know. No, I said they're friends. She goes, "No, they're not. They're flat earthers, aren't they?"
No. Give her a link. Get her in here.
That's it. Hey, Professor, I can see that you've got the same living room renovation that what Vlad had.
Yeah, yeah, that's right. Yeah.
Oh, I've seen that living room a few times.
You don't want to see inside my office.
How do you do that one?
It's fine.
Virtual background.
Did you have any comments for the topic we were talking about before?
Well, I didn't quite get there, but there's a couple of things I hooked onto. You were talking about relativity, so and I presume you were talking about time. Is that right? Time?
The primary topic was talking about rising Earth and how it doesn't work.
Yeah,
the things that
okay,
just don't work.
That's nonsense. Yeah. Well,
Do you want me to
I think
share?
if we,
Do you want a board?
I don't, well, yeah. I mean, if I can,
if you've got something to write on, do you want to bring up
yeah.
a board and I'll bring you up?
Oh, okay. No, that's a good idea. Let's just see. Go ahead. I can write. Yeah. Go ahead. Put a whiteboard up. Actually, I use.
Hold on a sec. I've got to
whiteboard
remove my
called-
thing to stop screen.
I
Now, if
use a
you want to
whiteboard
present,
Yeah. Okay. Hang on. You want me to do that? So what do
if
I
you
do?
add,
Sorry,
add a present.
Oh, down here. Yeah. Okay. Yeah. Good. And well, what am I going to present? Yes. What do I do next?
I don't know. If you just simply
I choose my own whiteboard. I can
Yes.
I can choose my own
if
whiteboard.
you pick something, it should come up on
yeah.
on my tray, but I'm not seeing anything on the tray right now.
Okay. No,
I have removed my paint thing from the screen.
Oh, okay.
So
Yeah, that's all right. I'll grab this.
Microsoft Paint.
Let's see.
Sounds good.
yeah. No, all I wanted to do was just draw and just do it on the fly. So
Yeah.
it's useful for
No, I'll
that.
tell you what we'll do. I've got another idea. Hang on. I'll just bear with me while I just fix this. Okay. Miro. All right. Now.
Ruffy, shall I just delete that link that you just dropped?
Sure. Yeah. The infinite loop.
You've been censored.
Oh no.
You've been censored. I'm going to put you in the timeout box.
Time out for 5 minutes.
Do you know, I was on Mikey's channel this morning, watching him drive and reading, and then steering and eating. And he put both my channels onto permanent block.
Yeah, he's not stable.
I didn't get timed
he
out.
needs to be off the internet.
I think so. It needs to take some time out.
Yeah. Yeah, if someone like Drunk Debunk just
Offensive.
critiquing him, he has a meltdown. Yeah, the internet's not for you at the moment, Mikey.
Yeah. Or ever.
Yeah. Oh, well, if he
no,
gets better.
not really sort of.
Crypto Rose.
Yeah,
I'm
sorry
familiar
for
with
that.
using Adobe Illustrator.
No.
Is that something that Professor Phil can bring up? Do you have
Yeah.
anything for me, Phil, at this point in time?
Yeah, I have. Just hang on one second.
that was
There's
just in
where you
response to
are.
Ruth.
Right, okay. All right. So
Oh, that was in response to Ruth. Okay.
haven't been on this stream
Yeah, the
live
link that you
before,
dropped.
so- Yeah. So present, and I'll do a screen share. Yeah. Okay. Okay. Share a screen. Which one? Oh, stats. That's good. Yeah.
Here we go. I can see something.
Okay.
now.
Well. All
Okay.
right. All right. Just ignore that stuff that's on. That was a previous lesson. Learning some statistics. See that? You want to answer that question?
New hair
New
salon.
house salons open the shopping centre. Customer numbers for the first 3 days are shown. If fit a straight line to the data, I'm pretty sure you guys can do that. Yeah. Right.
How good is
problems at all.
Excel?
Business is getting good.
Okay.
Gets better and
What else
better.
did they have? Oh, look here. They had to fit this question 10. Fit there. Oh, yeah, there you go. So we'll just use this space. How's that?
That kind of tells me that Monday is a bad day for hairdressing.
Okay. All right. So, all right. Let's talk about this gravity thing. Okay. Well, first of all, if you were explaining gravity in a really simplistic way, then you could say, well, let's say I had an object over here. Whoops, how did I do that? Hang on a second. What did I do with that? Let me get back there. Okay. What can you see on the screen still? You're still seeing the
We're seeing
the same screen, or has it changed?
a board that's ready to go.
Ah, okay.
It's
Yep,
empty.
yep, okay. I'm just wondering how I managed to get away from it. That's all. Where is it now? I got so many things open. That's my problem. Okay, where is it? Damn it. Yeah, you are. I can see you. Good to go. And I managed to screw this up. 1 second. Sorry.
That's okay. If you want a little bit of time, we can have a chat.
Yeah. No, have a chat while I just walk.
Is anyone seen anything hilarious in the last 2 days?
I'm gonna shut down some of these things.
Apart from Mikey crying and saying that the
I try not to
should
laugh at
die.
Mikey. Yeah. I try not to laugh at Mikey.
The Flat Earth Round Table is a back.
Oh yes, the Flat Earth Round
mean,
Table. Yes, and as you said, sorry. Okay.
Sorry, I think
Mumbai
my,
Cake said that
my
that's
chat-
closed down. Rose, I'll mute. Rose, did you want to say something?
I think I'm a lot more delayed than you guys because I think there's a huge delay, so I end up talking over you guys. So I'll just mute myself and shut up.
That's all right. If you want to say something, just you got 10 seconds, 20 seconds, whatever. Just shoot. Let's hear
I'll say something. My bedtime's 10 o'clock. That's my.
Oh no.
Input.
Gonna go, yeah.
Okay, if you want to duck out, just duck out. That's fine.
Sorry, Phil. I would love to learn some relativity.
Now I found it. Yeah.
Anyway.
All right. Well, we'll.
All right. Good night, Ruth.
Come again, Ruth. Let's have a chat about it because that's a bloody interesting topic.
Indeed. All right. Good night.
Yeah. All right. Catch you later. So I'll hang around for a bit.
You sure your wife won't mind?
Yeah. No.
This is interesting stuff anyway, so we like to talk about this stuff.
Oh, well, I reckon, well, first of all, when he's talking about relativity and he's talking about time, okay? So if you imagine, so if we talk about something that's, let's say, let me get my pens. See, this is what I did last time. I'm trying to get this. Where the hell are the tools? I was trying to work that out. Maybe this isn't probably the best idea. Okay, just hang on a second. I'm just trying to work out. I had this thing working perfectly today, and then and now I can't get the bastard working at all. So don't know what I'm doing.
Is it because everyone's looking at you?
No. I'm used to everybody looking at me.
Yeah,
I'm used to everyone looking at me. They do that all the time.
Do you still educate today, or not anymore?
Oh yeah. No, I was. I'm mostly retired but I helped. There's a good friend of mine he's a school principal. You know, so when I'm not in India, I help out at the school. So today I was doing that statistics that you saw on the board. You know, this stuff.
Yes.
Okay, and also the physics. Okay, I hit the boards. Oh, let's see. What do we have? What do we got here? Okay. Oh, that's a bit of maths. Okay. Don't know if you can you still, what can you see on the board? Still the same thing?
Yeah, we can see all the calculations. The
I can see all
calculations.
Oh, okay. Yeah. This was unbelievable. You meet somebody who's like 18 years old, doesn't know basic indices. You know, and I'm thinking, how the hell can that be? You know, but there you go.
Well, I gotta admit, I mean, I was okay with this sort of stuff back when I was in high school, but now I'm an older dude. I have forgotten about most of it because you know, if you get off the bike for 20 years, you tend to forget about it. I'm sure that I should be able to figure something out.
Can you see that question?
Yeah, the momentum of an object is the product of the mass and velocity object. Yep.
Yeah. Okay. So, so there you go. So F equals the change in momentum over the change in time. You know, Flatzoid loves this word impulse. He doesn't have a clue what it means, but he loves it anyway. You hear him using it a lot. Actually, I taught him that word, and then he's used it forever ever since. But he still doesn't.
Can you refresh
what
me
it means
on your definition of impulse?
Oh, okay. So as you can see, so impulse is really the change in momentum. Okay. So let's say, for instance, two cars heading towards each other smash on, you know, head first. Let's say, okay.
Mm-hmm.
All right.
Yep.
So they both have momentum, and impulse. So impulse is what is the change in momentum when they finally strike each other? What's the change in momentum? That's called impulse. Okay, so the change in, and as you can see, it's actually when we say the change in momentum, what we really mean is the change in speed.
Yes.
Okay, so obviously they come to a halt. You know, both of them, and they transfer all the energy from all that speed. They transfer that into the wrecking of the car, okay, of both cars.
Would you say that is a heat or?
Yeah, no. Well,
is mostly transferred in heat.
Heat energy. Yeah, no, it'll be mostly transferred in deforming deforming the panels of the car and throwing the engine around and breaking stuff. You know, that would be where most of the energy goes. Some of it will be in noise.
Oh, yes, noise. Yep, of course, yes.
And quite a bit of it will also be in heat, but nothing. Those two things would be really, really tiny compared to the crumpling of the the sheet metal. So that's really where all the energy goes.
Yep.
So you can see here in this. So this is a physics class. You can see here. So 12 kilogram car collides. What's the change in momentum of the car? So this is a kind of thing that police would be asking. You know. So I don't know whether the police themselves would be trained to do this, but they'd certainly be calling someone who is, who'd be able to answer this exact questions, right? So what's the impulse in the car? What's the average magnitude of the force? You know, if the car hit a wall, for instance, you know.
Yes.
Those are the questions that they learn, and you can see over here there's the solutions to those questions. Anyway, I was going to explain to you the there you go, my pencil's come back again. So what do we got here? A plus. Okay. Let's see the plus there. Pen. Oh, pen. Pens. Okay. Now I've just got to move that up. Oh, that worked. So
are you doing with a mouse or a stylus?
Do with a mouse. That's really hard to do with a mouse. Yeah. So
yeah, it'd be lovely with a stylus and a tablet.
Yeah, no, yeah, I got that. I got it at work, but in my office, but at work, but I haven't got that here. So I saw, but I'm not too bad with the mouse, but it's really hard to do, you know, as you probably know. Okay, so let's see if I can move all of this up. Oh, what do we got here? Yeah, that's right. This is. I was explaining to the students I said, you see how this is here we're looking for the see, we've got force and time, right?
Yes.
We've got force versus time. So if we were looking for force over time, then we'd be looking for the gradient of this line at some stage. And the way to get the gradient of a curve like this is you'd have to get the gradient at a particular point. I mean, so that's why those stupid flat earthers say, "Oh, you can't get an angle off a curve." Well, you can find the spot where you want that, where the tangent is to that curve, and then take it down to the origin. You'll have the angle. I don't get. So anyway, so that's what this is, and then so the area underneath is that's if you're multiplying things. So if you're multiplying force by time. Okay, force by time, which is impulse, and then that's the area that's underneath that curve. All right, let's move on. This explains the momentum. So you can see the large one moving. So that's the momentum of A, momentum of B coming towards each other.
Yes.
All right, and so you can see that you add them both up. So if one thing's coming from one direction at 20 kilometers an hour, something's coming from at 40 kilometers an hour from the other direction, they smash into each other. They smash into each other at 60 kilometers an hour.
Yes.
Okay. So you have to add those two momentums up. Okay.
Yep. And
right.
Is the mass of A and B in this equation or not?
Yes. So
yes.
in this case, what we're showing you, the mass of A is bigger than B. So what's going to happen is, because the momentum of A is big, even if A was going slower,
yes,
right? Even if A was going slower, right?
Yes.
Finally, it would still end up going back in the direction that A was originally going. So in other words, so B would have to be incredibly fast to overcome the mass that A is.
Yes.
Okay. All right. So
that's why B is going to be a little pocket rocket. That's why.
Yeah.
It has to punch hard.
It has to punch really, really fast to be able to. And usually that's not going to happen, because what's going to happen is that B will find its way through A before it actually manages to stop A, because it's so huge. So a little truck running into a little car running into a truck does not have a hope.
Yes.
Okay. Because you've got this, the truck will still keep pushing the car along even after it's all smashed up into pieces. So that's what what that's showing. And then of course we've got this. So the students had to. So sometimes we train the people who do the police stuff, and they learn how to. We teach them how to work out how fast a car was going on a road. Because all they've got to go on is they got the car, and then they see skid marks and stuff like that. So we show them this is how you measure. You can deduce what happened in this particular accident, because usually in big accidents there's nobody there to tell you what happened. Well, they are there, but they're not able to tell you what's happened. And then I use this for a bit of chemistry over here as well today. So that's.
Can I ask you a question on that particular part before you roll on? I was listening to Vlad's channel in the last half an hour or something, and Harlan was going on there saying, "How do we even know, that hydrogen and water actually exist, and if they're even in water at all?"
Yeah.
How do we know? How do we zoom into such things?
Oh, perfect.
Do you have any insight on that?
Yes, absolutely. All right. Now I can actually draw now on this thing, and I'll show you exactly how that's done. All right. Actually, it's the magic of chemistry. It's fantastic.
And the first thought I had was electrolysis, but when we even talk about electrolysis, how do we even know what oxygen?
That's exactly the answer.
Yes, but I think that he was going into in a much deeper format of how do we actually know? How do we actually even identify what hydrogen is in the first place, to be able to then move on and identify what oxygen is in the second place?
All right. Well, okay. Well, that's a good question. because we're looking at, and we're saying, well, what would be first of all, what's the properties of hydrogen? Okay, all right. So we're looking at that, and we say that well, we know that protons, electrons, protons make up, and neutrons make up atoms. All right, and we know that these days we can actually see an atom, and we can tell what they're made of by the relative masses of the constituent parts of atoms. So we know that hydrogen just has one proton. Normal hydrogen has one proton. Heavy hydrogen, like deuterium or tritium, have also got a neutron, and tritium has 2 neutrons. Okay. Now, all of this is empirical. It's measured. All right. So this isn't something, wow, this is a model that we just dreamt up. Okay. Now, how do we know that it's hydrogen? It has certain properties that tell us that it's hydrogen. First of all, 1 gram of it, we can, if we say fill a balloon that contains let's see, what is it, 24.8 liters, with a temperature at 25 degrees, and the pressure, the normal pressure of 1 atmosphere, and we put that on a scale, after measuring the taking away the mass of the balloon, we notice that it weighs exactly 1 gram.
Okay.
If it was helium, it would weigh exactly 4 grams.
Yeah.
So we know that property. 1, we can burn it. 2, we know how much it weighs. So there's 2 properties that we know that belong to hydrogen itself. Okay.
Yeah. Does that put a color at all or not? Or is it 100%?
It certainly does. So when you burn it, yeah, absolutely. When you burn it and you look at it through a spectroscope, you notice that it's got the absorption lines for hydrogen. So you can see the absorption lines for hydrogen. And by the way, when you look at that same spectroscope and look at the sun, you notice it has the same stuff.
Okay.
If you look at a different element, you can see a different stuff. You say, well, all right, well, sodium has this absorption spectrum. Krypton has this one. Argon has a different one. They all have their own signature spectrums. So therefore, exactly which element you're looking at.
Okay. Can I ask a quick question?
Yep. Go on. Sure.
In terms of weight, you mentioned that that we would fill a balloon, we'd know it's exactly 1 gram.
Yeah.
How have they come to the point where they actually have counted the amount of particles it is to be able to, so the amount of elements that are actually in there, to be able to know, okay, we've got 10 million hydrogen atoms, and that equals 1 gram. So like weighing a single hydrogen atom is impossible, isn't it? And so we would need to say we know that this can occupy 1 trillion hydrogen atoms or something like that, and then we can divide it by 1 trillion, correct?
Yeah, exactly.
How would that come about?
Okay, now I'm just trying to work out why I'm not all right. Well, the number you're thinking of is called Avogadro's number, okay? And Avogadro's number is, I'll write it down here. So 6.02 by, I have to watch my bad handwriting because of the mouse, 10 to the 23, okay? Okay, so 6.02 by 10 to the 23. That would be of that many atoms, that many molecules of hydrogen. Hydrogen goes around in pairs. That many molecules of hydrogen,
yes,
okay, would have a mass of 2 grams. Okay.
Okay. And is there a specific units they put it into? Obviously, they're not using standard happy birthday balloons. Is there a scientific container that they put into jar?
Yeah, we have things called gas jars, which
gas
are
jars
specifically designed for gas. Yeah,
yes.
For gas. They're called gas jars. Yeah. So yeah, no, we don't have to chuck them into specific balloons. We have there's ways of especially measuring them like that.
Yeah, because I'm thinking to myself, if it was 200 years ago or 300 years ago, how would I even start to even figure out how to measure what hydrogen is to even start the periodic table?
Oh, look, you've got to hand it to those people who did that. I mean, they, with so little, compared to what we have, and those people managed to do that. It's just absolutely unbelievable, what they managed to do with so little. So they did have gas jars, and they had round flasks and things like that for which they were able to collect gases. For instance, if you collecting a gas and then making sure that it's the only gas you got is actually not a very hard thing to do. For instance, if you're collecting hydrogen and you keep hydrogen coming into your gas jar, and so that it's had sufficient time to push everything else out, okay, then you know that you've got a gas jar that's full of hydrogen.
Yeah.
Okay.
Surely there must be a couple of gases which are kind of stubborn and they won't like to be purged so much. I mean, I'm sure that you could swirl it inside and stuff.
Yeah, look. Oh, look. If you keep the pressure up and just keep pushing it along, and give it enough time to get it out. If you've got more energy in and more momentum, like we were talking about before, in the stuff that's coming into the gas jar, then you're going to force the stuff out of it. Okay, so gases are not so different from each other that they'll say this one is like this particular gas is so heavy that the other one can't push it out. Okay, they're not like that. Okay, so gases are very, very close to each other in terms of both their size and the way they'll behave. For instance, otherwise we wouldn't be able to have things like the ideal gas equation. Okay, where we can say, well, and using the gas constant, for instance, like 8.31 wouldn't be a useful thing a useful constant if the gases were so vastly different.
Phil, I think they were using some sort of gas to find the absolutely zero temperature as well. They threw lasers into this gas to slow it down to a certain point to reach zero, but even because they had some movement, it still couldn't get to absolute zero.
No, that's right. That's so that's, I mean, theoretically it's impossible because then what you have to do is to be able to say, well, how the hell are you going to stop electrons from orbiting the out of electrons that orbit the protons? How the hell are you going to stop them? Because as long as there's some energy, you can't get to absolute zero.
Yeah.
So we've got really close, though. I've got to tell you. I mean,
I would have thought also if you're in a situation where you've taken something to extreme vacuum, then you've got nothing to shoot at to be able to measure. Is that correct?
Yeah, that's a good point. Yeah. No, that's.
I mean,
that's a good point.
Like, I know it's very hard to get absolute vacuum, but if you pushed it to such a point where your laser only gets struck by an atom once in a while, you've got nothing to measure. So you could never really truly measure what absolute zero is.
No, you wouldn't. The thing about it is that, that in itself, this idea that you have to is your instrument is just as much a problem as the gas itself and the movement of the gas.
Mm-hmm.
Okay, how accurate is how still is your instrument? Your instrument's moving as much as any of the gases are in when we're talking about that sort of vibration.
Yes.
Now the other problem is the other problem is creating this vacuum in the first place. So when you try to, you've got a gas chamber and you've got two surfaces that join together in order to make it to seal it, right? The seals, the materials by which those seals are made of, are larger. The spaces between those seals are larger than the gases, are larger than the molecule, than the hydrogen molecules. So we're talking about over time, it's inevitable that you're going to lose the gas. Because
so if you've got a metal and if their atoms are very large, the hydrogen atoms will squeeze through the cracks, either inward or outward.
Yeah, exactly. So you're trying to pull stuff out, and stuff from the outside is getting in, and you can't stop it because you can't make a seal smaller than the hydrogen atom itself.
Yes.
Wow.
If only we could just magically tell hydrogen to become steel.
Ronnie could just tell it to get bigger.
Yes,
that'd be good.
And when things get to zero or near there, the strange things happen to liquids like mercury and other gases.
Yeah, so we've got these super fluids, and yeah, exactly. Yep, yeah, they do. So we have strange things happen with their density and stuff like that. So yeah, we're talking about stuff right on the fringe. And by the way, very, very expensive stuff to work on, to experimentation. So you don't see it often. So usually in science we have, it's not often that people commit a lot of money just for the sake of trying to discover, absolute zero, for instance,
Well, they spent a couple of $1 billion on the.
Usually, what happens when you're going for a grant? When you're going for a grant, someone wants to see a return out of it.
Well, if they want some of that money, maybe they should cry on YouTube once in a while.
Yeah. Well, the problem is that someone would say to you, well, if you're going to do this research, what's its final benefits? What's its benefit to society? And where we say, well, knowledge, you have to put up a case, for why is that? How is that knowledge beneficial? In what way would society benefit from that knowledge?
What was the case for CERN then, Professor Bill? Because that cost a couple of $1 billion.
Sorry, the
CERN facility where they did the hydrogen.
Oh yeah. No, that's extremely important. That's extremely important because we're looking at the quantum world in this case and saying, well, how can society benefit from that? And clearly we can.
Okay, I'm a little bit behind on. Sorry to interrupt. I'm a little bit behind on on how CERN is actually benefiting people right now. So, what can you share which CERN's discoveries in splitting atoms is okay, like helping?
Well, it's splitting atoms is definitely a thing that we need to do because that's our nuclear fission work.
Yeah, I'll take that one back.
Yeah. So yeah, but smashing atoms into each other and maybe creating a new element. Or working at how we can develop different ways of producing energy by doing this.
Yep.
There's a whole bunch of stuff that we can learn by smashing protons into each other or smashing electrons. All of this work that we've got, all the stuff that we use, LEDs, the stuff that we've done with light, using light to discover new minerals. For instance, now you can actually get a gun, something like a gun, shine it at the mineral, and it tells you what it is.
Wow!
How good is that? It's just
pretty amazing,
incredible. It's just like Yeah, it is. It is amazing. You know, I mean, I'm thinking back to the days when I first graduated. You know, when actually I went into chemistry because of all the glass and all of the, it was really, you poured this liquid and all these fumes and and yeah, it was a lot of fun. Chemistry, and I was in a dangerous part of it because I started off in explosives. And, that was extreme. I have one.
Can you answer me one question?
Yeah, go on.
Yeah, you go on. Finish what you were saying.
I was going to say I have one of only a handful of Victorian licenses given out back in the early 70s that allowed you to make and use explosives, provided that you did all of the stuff. Mm-hmm. So I got given that, as a young chemist, because I was working in the area, and I actually have this little red book, little red thing, hardcover, with a license on it, stamped by the Department of Minerals and Energy, by the Department of the Geological Survey, whatever they were at the time, stamped by them saying that you are licensed to actually make explosives.
Crazy.
Yeah,
that's wild. That keeps you off the terrorist watch list, doesn't it?
Yeah. Yeah. I shouldn't be saying that. Actually, you never know who might knock on my door. Anyway,
well, they know what your living room looks like now.
Yeah.
So they should be able to tell. They should be able to tell that by the shape of your house. The question I was going to say was, what is the color of radio waves?
Oh, okay. So. That's I don't think radio waves has a color, does it? It's, if it had a color, it'd have to be towards the red spectrum, obviously.
Yeah.
Because
I'd say it'd be so far off the spectrum from a color perspective.
It's not in the visible light spectrum, so
no.
So
you'd be able to detect it with a
computer. Doesn't kind of make sense. It's radio waves are so far from visible light in terms of it's like it's like kilometers to nanometers, like that. So, and if you think about, let's just think about how small a nanometer is. So the wavelength of a wave, right? So in other words, from one crest to the other, right?
Yes.
When you're talking about visible light. So, so right at the far end, we're talking about 750 nanometers. So a nanometer. Take a millimeter and divide it into 1,000. Okay, that's only going to give you a micrometer. Now take a micrometer. After you've divided that millimeter into 1,000, take 1,000th of that and divide it into another 1,000. Now you have a nanometer.
Wow, that's pretty.
And the wavelength, the wave from one crest to the other, is that small. Compared to radio, where that could be a kilometer long, wide. From one crest to another is a kilometer. We're talking about a nanometer. That's one crest to another.
Yeah.
So in other words, 1/1000th of a meter. An incredibly small amount.
So how did Germans figure this out in their Heckenheim thing when they're trying to do the beams to go to bomb London and stuff back then?
Oh, look, you think you got to read the history of these people and read their papers, because I'm telling you that it makes my blood boil when people say, when the stupid flat earthers say, that Newton was an idiot, or this guy was an idiot, or that guy was an idiot. And I said, you don't have, pardon my French, a fucking clue.
Yeah.
Right? You if you only knew a fraction of what's involved in what this person discovered, you would never say something so stupid.
Well, Newton came up with calculus, didn't he?
Yes. And you think
about quite a few things.
He's 24 years old. He's working on this thing because, I mean, one of his problems was that, even at university, even in first year university, for instance, we and certainly in high school when you're teaching physics, you're really looking at constant acceleration. You're looking at linear acceleration. You're looking at linear velocities and stuff like that.
Yep.
Newton knew that this wasn't what real life was, right? You know, things were curved. You know, you had things went around in orbit in eclipses, in ellipses. You know, like I mean, that's what discovered by Kepler. You know,
yeah.
Well, you had to have calculus to be able to work out those trajectories. You know,
but calculus wasn't invented before then. See,
I mean, you know, the thing about it is, before then, they you know, like someone like Kepler would look at. Kepler actually came up with the important ratio of r cubed over t squared, but it was still, that was simplistic compared to what Newton had to deal with in terms of gravitation, and therefore needed the calculus to be able to do the work that he did. Okay, and developed it in order for him to do that gravitation. You know, and you know, they say, well, Newton didn't. I hear stupid stuff like, oh, Newton didn't want gravity ascribed to him. That's actually pretty dumb. What Newton was basically saying in this case was that I don't know why gravity does what it does, but I sure bloody know what it does.
Yeah.
Okay. Oh, there you are. You've got the electromagnetic spectrum up there. There you go. And that's just
I tried to.
That's just the extent of visible light. Okay.
Yeah, I was going to ask a question because I was looking at this and you sparked my thoughts. Is it possible that the only reason why we see the visible light band, right, is because, like, I don't know what. So 400 nanometers to 700 nanometers. So the wavelength enters our eye at a certain size, and that's what comes in best. And so if it was 1 meter, that would mean that the wave would pass up above our head and down into our eye, but then up above our head, and so we do not consume the light correctly. And with the X-rays, with the ones which are 0.0001 of a nanometer, the wavelength is so small that it's almost a thin line, and it doesn't go to the receptacle, the receiving end of your eyeballs.
Well, if you think about it, that in terms of that size of that, first of all, if the wave was any bigger than your pupil was possible, that you certainly wouldn't go through it. Okay.
Yeah.
So that
it's just splashing all around us, but it's not entering your eyeballs. Right. It doesn't go into your pupil like at all in one whole unit.
It has to fit. Okay.
It has to fit. It has to fit through the hole. It's like a pinhole.
It's got to fit through the hole. Yeah, exactly.
Good.
It's got to fit through the hole.
That's a good one. That's one thing I can go and tell to that guy who says you can see radio waves. That radio waves is 1 centimeter to 1 meter in width, and that we need an eyeball which is 2 meters diameter, don't we? Or maybe even 10 meters diameter.
At least.
There we go. Because if the hole inside the front of your eyes, in front of the pupil, is like, let's say it's 20% of the width of your eyeball, you would need an eyeball which is 5 meters or greater.
Yeah, precisely. The wavelength is larger than. Yep.
No, it's fantastic. I hadn't thought about that, but now it makes sense.
Yeah.
I mean, how the eyeball evolved to where we can actually see things and. Wow.
Well, now it's things like that are the only things which actually make me think that maybe there is a God.
Yeah.
Maybe. Yeah. It's the fact that how on earth did we evolve to the way we are right now? I just don't know.
Well, look, the thing about it is that it's like saying that the world, if you were religious, you could say that the world was made for us, right?
Mm-hmm.
Now, but look, the other side of the coin is the world was made, and we fit into the physics of it.
Yes.
Yeah.
Force. In other words, we had to change. We had to evolve in order to fit into the the ecology and the surroundings of the actual Earth and all of the properties of all of the stuff that's around us. Gravity, for instance, where the shape we are, we couldn't be different because gravity forced us to be like this.
Yes.
So,
yes.
so
if gravity was like 3 times the strength, we'd all be like crocodiles, like scratching on the ground.
Light existed long before we turned up. So we had to adapt to the idea that if to survive we have to see things around us, then we have to have a pupil that's small enough so that stuff can get through it. Okay, so that would have been part of the stuff that we would have had to develop. So there was one time when I actually asked myself a question, right? What if light and sound were inverted in a way where, what if sound traveled forever and light had a short distance? So we couldn't see space at all, but we would hear, our eardrums would explode all the time from all the explosions of supernovas throughout the universe. Imagine that. I just had, it was just a thought pattern which came into my head. Just, entire universe is exploding and crashing together, all smashing our ears, but we can't see any of it. Well, it's happening. You're quite right. The only reason that your ears isn't being bashed by it is because there's practically nothing between that explosion and us.
Yes.
And sound needs the medium to travel through.
Yes.
It doesn't have it.
That's right.
Okay. So all of that noise has to be happening because heat, because sound energy is going to happen if there's, things get vibrated. But there's nothing in between them and us, so you're not going to hear anything.
Yeah.
So what about when they?
If there was enough particles in it, we'd definitely be hearing it. In fact, it blows away.
Yes.
Didn't they put a microphone near to the sun and recorded the sound it was making, or something like that?
I think that's electromagnetic.
Yeah. Look,
right, like wind.
Could be, right.
Yeah.
I think it's solar wind.
I'm not. That's this astronomy is not my thing, but yeah, as far as I know, anyway, it was not the it was not that. I actually one point in time I wanted to do a video about things like Star Trek and Star Wars, and about how most of the things are flying through the sky, shooting each other, and you're hearing all the explosions of all the ships exploding and stuff, and how it would be the most silent and very uninteresting war you would ever see in the sky. Yeah.
And I mean, even the fact that most of these ships, they make them fly. You will notice this as you look at most movies, right? And we know that's how fictional they are, right? Is most spacecrafts in movies will fly like an aeroplane. They are not in a position where they accidentally turn 180 and they're still falling backwards. You know what I mean? They don't have that problem. They turn and their velocity changes with that new vector.
Yes. You're right.
I think there's a game I played on.
I wanted to. Yeah, go on.
There was a game I played on at the places I used to go to, Space Invaders or something like that, where the ship would take off and fly around and you'd knock off, and it was fairly close to actual physics of a spaceship.
Yeah.
So,
I was going to say the spaceship is. I mean, that is still a very, very rudimentary thing and moving extremely slow compared to most things in physics. But yeah, I was going to explain this because I heard you talking about the gravity before, and I was going to explain this to you. So often you hear people say, "Well, what is this space time?" And you say, "Well, why is there space and then there's time?" Well, if you take a pen and you move it from here to here, okay, and it moves across there. So what would be what would be properties of that? You'd say, okay, what are those variables? Well, one of the variables was distance that it traveled. Yeah. What's the other variable?
Well, the time for the pen.
The time
would be
the
time for the pen would be resultant on the pen.
If there wasn't a time, it didn't move. Yeah. You needed the time. So you can now say that both the distance and time are intrinsically linked, aren't they?
Mm-hmm.
Right. Yeah.
You can't have one without. You can't have something in motion from here in motion that moves from one place to another without time involved in it.
Yes.
So time and distance are intrinsically, and time and space are intrinsically linked.
Yes.
So if we can talk about those things, it's almost impossible to talk about distance without talking about time. And if you're talking about something that's moving, it's impossible to talk about something that talk about time and movement without talking about the distance. So they're intrinsically linked. So let's put those two things together, and we'll say, well, assuming then let's look at time as a continuum and say, well, okay, well, that doesn't all by itself, so without any other influence. Okay, so we know time is a thing, it exists, and we know distance is a thing that can exist if you make it exist. All right, well, in its purest form, both of those would be uniform. Okay, because there's nothing that's affecting them. But what we have
both distance and time?
And yes, both distance and time, both position and time, and time. All right, position and time. They are uniform. So in other words, and that's depicted like a uniform fabric. It's an analogy. Okay, when they talk about the fabric of space time. Okay, that's because what we're looking at is something that's pure, unaffected by anything else. But what Einstein worked out is that time does change. Things can cause it to not be uniform. For instance, we know that time does change because we know the satellite up there, if it's moving that's moving fast enough, the clock on it, the cesium clock, the clock itself doesn't change. Okay, time changes. Time itself changes. Right, that cesium clock doesn't tick any faster or slower than what it is. It's time that's changing. All right. The people who, if someone was there in that spaceship, like for instance the ISS, someone's in that spaceship, to them that clock's working perfectly well. It's not slowing down. And then when they are accessing our clock that's on Earth, it's slowing down.
Amazing.
Okay. All right. So it's time is actually slowing down. So this is something that's worked out. So that time can be changed, can be warped, and also space can be warped. So Einstein's field equations is really about describing the extent to which the space-time will warp. Now, anything moving through this influence. So as something is warped by, let's say, the Earth, something huge like that creates this warpage, if you like, for want of a better word, and something's moving through that, it has to follow the curve of that space-time that's being created by it. It's that area, that part is called Earth's gravitational field. So let's not confuse Earth's gravitational field with acceleration. Acceleration is not that. Acceleration is the tool that we use to measure the gravitational field. Because what Galileo and Newton figured out, they knew that there was something there. They didn't really understand it like Einstein came to understand it. They knew there was something there, and it was always, well, how the hell can one know that it's there, and two, measure it? Well, Galileo worked this out, because what he did was he worked out that regardless of the mass, they accelerated at the same time. Things accelerated at the same time. The key to understanding and measuring this gravitational field was the acceleration. It was the thing that we could say, right, okay, that's what makes it. If the gravitational field changes, the acceleration changes. Well, that's the thing we can use to measure it. So the gravitational field, we talk about that in newtons per kilogram. Acceleration, we talk about that as far as distance and time, so in meters per second squared. Right? They're totally different things. That's why people say, well, we say that acceleration is gravity. No, it's not. The gravitation is the field. This thing that you're measuring there, that's the tool that measures the strength of the gravitational field. Yeah. So if we take a gravimeter to a spot somewhere in Western Australia or whatever, and we put it on the ground, and we say, right, okay, well, the acceleration is different over here, therefore the field is different, because the acceleration is measuring the gravitational field. If we take it somewhere else, it's different. The gravitational field is different over here. So now, so that tells us that the density of the stuff beneath that is different. Yeah. Because one thing that Newton did work out was that it's the mass of the thing that influences space-time. But now what's the big question, and why does people like Neil deGrasse Tyson or other people say we don't really know about this gravity? Because you know what the fundamental question that's not been answered is, why does the mass change the gravity? Why? Oh. Okay.
I don't think I have an answer. No chance.
Yeah. Yeah. This is what we're searching for gravitational waves for, you know. Right, this is what we're searching for. This is the big questions that are still, you know, not quite answered.
I mean, like you mentioned about the gravitation thing device and I think PhD Tony uses that for his mining and stuff like that. But someone invented that, Phil, right?
Yes, yeah. And what did they invented it with the knowledge that Newton gave us. Okay, and you then said, right, okay, well, we'll test it out. Does it actually do that? Well, that's a perfect example of evidence of a gravitational field. Because why is it different there? If it was something else, why is it? We can put this over here and measure the acceleration is different over there, and that acceleration tells us the nature of what's underneath the ground, deep underground. We can tell what's deep under there.
And to put it simply, I think
a submarine can navigate and past mountains and rocks and stuff like that. Yeah. You know, by using again the gravitational field that's those things present.
And I think the simpler way to equate that would be like when Critical Think did his experiments with his weight from where he lived to when he took it to Antarctica. When it's a very simple explanation of here's the weight, here's this weight scale. It's zeroed out in where he lives. Then he takes it to another place and it's different. The weight weighed differently. Why is it weighed differently? Because of the gravitation. Then he takes it to Antarctica. It weighs differently there. So he's got evidence that gravitational field does different things in different places.
Well, actually,
yeah. Sorry, but
let me just correct you a little bit on that. Okay.
Yeah, that's correct.
Yeah. Okay. So the gravitational field does change because of that, but he was not doing that. You see, he was using because rotational speed is F equals ma, so mass times acceleration. Okay, and acceleration is in circular motion is v squared on r. Okay, So what was happening is he's measuring a different. He's measuring. This is what he's measuring. He's measuring the v squared on r. That's what he's measuring. It's the rotation of Earth that's causing this. Okay, not the gravitation. The gravitational does, but it's insignificant to what compared to what he's measuring when he's measuring the rotation of Earth. Okay.
Yeah, he was trying to judge the centrifugal force. So
Okay.
if you're
Yes,
at the
that's
equator, the centrifugal force is the greatest because you're
mv
spinning the
mv squared
furthest.
on r, basically.
And the 1 kilogram item is lifting higher off the scales, whereas down in Antarctica, whereas almost like sitting still from a rotational perspective, it's just dumping on the scales heavier. That's what it was.
All right, so
From a simplified perspective.
Yeah, exactly. Yeah. So yes, he that's entirely true. Yeah, exactly. So critical thing was actually measuring the rotation of Earth. Okay. And very effectively too. So that was a great. The other great experiment that they did over there was the one by MC Toon. That was brilliant. That was the one that was where he had the sundial on the ground, you know, and that was, you know, I mean, that's historic. I doubt that's ever been done before like that. So that was definitely very, very historic.
And the geometer, that was pretty good too. Pretty cool.
Sorry?
The geometer, the thing in the box.
Yes,
yeah.
Oh, absolutely. Yes, the whole thing was bloody good, right? So, but you know, if you had to single out two of them, you had to single out two of them and say for sure, you know, because this over here unequivocally proves that the Earth has to be a globe for that to happen.
Yeah,
it absolutely, there's no way to avoid that, because this could not happen in under any other circumstance than he showed. That had to be a globe that does that, no matter what. And
what if he resets the scales each time?
Well, that's what that would have been really helpful. He obviously he wanted not even having a clue how that works, you know.
Yeah, completely clueless.
Not even a clue. It's just laughable how you know what he said. That's just ridiculous. You know, I was just thinking, because it was like 2:00. I don't know what time it was when they started that stream, but it was around about that, probably be about 2 p.m. for us, you know. And he's standing, and those kids, they kids to me, everybody's a kid is less than about 50. They are standing at Punta Arenas looking south, and they see that the sun is down there.
Yeah.
Yep.
Well,
light bulb.
While the sun is down there, the sun is over us here in Australia. At midnight. In fact, it's right in central, right over Darwin, right over Alice Springs.
Yep.
Right? That's where the sun is, while they're standing in Punta Arenas looking directly south. You have to be a complete fool to not say, there's absolutely no point going all the way to Union Glacier to see it, because you know what's going to happen.
It was half solved.
Sunk.
It was half solved, at least. I mean, going to Union Glacier was still a defining moment, no doubt about it.
Oh yeah, for
but
sure.
The question is why, even though Whitsett's come back and he doesn't seem to want to talk about anything anymore, he's pretty much missing. He's missing an action. He still thinks it's flat, because I don't think he wants to swallow the bullet. And Elizabeth is trying to get on the bloody channel or whatever. What's his name?
Yeah,
Mark Sargent.
Yeah.
She's actually just seen their cardboard cutout. She actually didn't get on the show. She's been cut out. Mark Sargent printed her out on a board, and then plonked her in a room. He plonked her in the spare room, and he's talking to her
actually there.
Cardboard cutout.
Okay.
She wasn't there, but she didn't say much.
Nah, she's
well,
never
I was just thinking.
Okay,
so I was just thinking that I'm actually producing a video, so I'll let everybody in on it. I'm actually in the throes of doing that. It's just a really busy time at the moment because we've got academic year just starting now, and I'm actually doing a video, and I'm saying this is the education of Whitsitt and Lisbeth. I'm actually going to talk to them, and I'm going to say, you saw this, so you can't be like Flatzoid and Oakley and that, right? You saw this.
Yeah.
You actually saw this with your own eyes, right?
Yeah.
Let's talk about what you saw.
Mm.
Let's talk about how the sun is going around Capricorn, okay? And you saw the sun all the way south there, looking south in a southerly direction, while if the Earth was flat, would be in the back of your head.
Yeah.
Okay. And I'm going to say, and here is what Flatzoid did himself. He went on his holiday and watched the sun rising south of west,
which is impossible.
While the sun, while he knows that there is no way for him on a flat, if the Earth was flat, for him ever to see the sun while he's facing anywhere in that direction. He'd have to be turning around, looking north to see it.
So,
Lisbeth, you can see that. You are you stupid or what?
So I've got a question for you, Phil. Like, I've seen quite a few of your videos and stuff like that. When was the first time someone said to you, there's flat earthers out there? What was your immediate thought?
I still get people to come that because the things turn up. The immediate thought is that's ridiculous. They just having you on. In fact, my wife still doesn't believe it. She reckons that they just pose.
But you've debated a few of them since then. I know you've actually talked to them.
No, I know. I it took me a long time to believe it. I just thought they were having fun, so I thought, well, all right, that's okay. I get that. Yeah. You can have a bit of fun by saying there's, the tooth fairy's a thing,
Yeah.
And I thought, but they they mean it. They the vitriol.
It's I don't. It's I kind of know what it's all about. I think that they feel special. They feel that they're in a community and stuff like that. But I mean, how it continues to evolve in a way where 6 months ago, everyone was saying there's definitely not a 24-hour sun. We can't have the sun rotating around like that. Every one of the streams now, you go on there and you have a look at it, and they're all saying the 24-hour sun in the south was never a problem for flat Earth. That's what they're all saying now. They've all flipped, all of them. And like 6 months ago, they would have said definitely not. Now it's not a problem. But I don't think you can ask them, why is it not a problem?
Yeah, exactly.
I'm sure they'll kick up stage.
Well, what? How can they say? How can you say it's not a problem? That's ridiculous. How can it be? Just like I just said, how can it be all the way down there? You must be looking across the continent, all the way to the other side, and Australia's over there.
Yeah.
How the hell did that work on the flat Earth? And then this idea that the AE model, we don't ascribe to the AE model, but yes, you do, because the first thing you do is you say that that navigation works. Well, that means you agree that the latitudes are concentric circles, don't you? Otherwise, navigation doesn't work. Then you agree that longitudes are a thing. Otherwise, navigation doesn't work. So, if the concentric circles are a thing, and you say that Earth is measured flat, this idiot Oakley says that all the time. In fact, writing a book that's saying that Earth is measured flat. So I said, if you look at Polaris from from anywhere north, then the ground is flat all the way to the GP of Polaris, which is at the North Pole. So you're saying it's flat. Well, if you move back to the equator and you're still looking at Polaris, if you could, then you'd still say it's still flat. If you move further away from the equator, so you're now heading south, okay, still flat all the way to the GP. So you've agreed that the damn thing is flat, and these concentric circles go around. How? Please tell me, how is that different from the AE map? By the time you get to 90 degrees south, how is that different?
I don't know.
I don't know, man. There's a lot of true Earth which actually have no clue what it actually looks like at all.
How can they not know? Because the ships and aeroplanes are flying around the damn thing all day, navigating wherever they're. So they definitely know where they're going, and they definitely know which direction they're going in. I mean, they don't stick their finger up and go, "Ooh, I wonder how much fuel we should take." You know, They know how far they got to go. They know how fuel they got. They know there's laws that govern this. How much fuel they have to have with them and all stuff like that. So they know exactly how it is. So they know how it is. We have GPS. What's your longitude and latitude? All right, okay. What's yours? What's yours? What's yours? Everyone knows where they are. Based on the longitude and latitude coordinates, right? So they must be going around in circles. So there's no different. They can't say if it's flat and then it doesn't look like they don't know that if it looks like the EMAP. You can't say those two things together. You can't say that it's flat and navigation works and then say you don't know what it is. That's ridiculous.
Well, I actually figured out how flat earthers, can get around without a map. Did you know how that they can get around without a map?
No.
No,
okay.
Go ahead.
Well, without a flat earth map, flat earthers need to refer to the have a sign formula, where they basically just simply follow the road signs on the street. That's it. They just don't even have a map. They just wait till the next road sign comes along.
That's brilliant.
Have a sign.
That's brilliant. I've yet to hear a flat earther explain if you had longitude. So this is again their navigation. I want Oakley to explain this. So you've found your fix, right? So you know your latitude and longitude. You think you're not lost. Now you got to go somewhere, don't you? You can't just stay there. You got to head somewhere, right? How do you know how far that other place is? Let alone which direction it is. How the hell do you know how far it is without using the Haversine formula or Vincenti's formula? How the hell are you going to work that out? If you know your longitude and latitude, you know the longitude and latitude of the other joint, how are you going to work out the distance that you have to go still? Is that something you have to guess? I'd like to see you do that on a flat Earth.
Yeah, but like the
without using the radius of Earth.
Yeah, but the longitude or latitude wasn't invented for until when they used a competition in England, and the guy created a clock and discovered latitude.
Hold on a second. What year?
Longitude, whichever one was.
because I think. Didn't
actually
you say something about this?
Came up with that.
Okay. Yeah, didn't you say it's like 300 BC?
I actually around about 160 BC.
It was earlier than what I thought.
Oh,
yeah.
It actually predates the chronometer. I think the chronometer is the correct name for the correct clock.
Yeah.
Yeah, so basically that's when that came up, and it was a very simple thing because they didn't know the Earth was a plate; they just thought it was a sphere. So they divided into 360 this way and 360 that way, and made a grid. It was that's all there was, and so it's not by coincidence. I'd like to know why it's degrees. When you get past the equator, and you're not pointing at Polaris, where you getting why does it stop at 0 at the equator and then it carries on 10? Where do you get that 10 from? Where do you get the 20
Well,
and the 30 and the 40 and the 90 from? Where do you get that? Because you can't see Polaris to get it.
Yeah, I said to Shane in a comment, I said if we've got 90 degrees of declination down on the left and 90 degrees of declination down the right, and then we've got a negative 90 degrees of declination on the bottom, another negative 90 degrees, you add 4 times 90 together, you end up with 360. And then when you calculate how many longitude it is around the outside, that's 360. So it's like, what's 360 by 360?
Yeah,
I think it's a sphere.
It is. It has to be a sphere.
And it has to be a sphere.
And that's why they can't. That's why they can't use latitude and longitude to find distance, because it's going across. It's going over a sphere. It's going. You have to have the radius of that sphere to be able to work out that distance. Otherwise, it's impossible. You're working out an arc. How the hell are you going to work out the distance over an arc without knowing the radius?
Well, another thing, Phil, is like when they bring up the dome, right? So I ask him, what happens if you have 2 domes together? What's that make? A sphere.
Yeah.
Uh-oh.
Yeah.
Careful with that.
Look, I'll be honest with you. All of my colleagues think I'm very, very eccentric. They think, Phil, it's got to be your age.
Right.
I said, what do you do when you go to the country? Do you stand at the farm gate and yell at donkeys?
No.
Because like just for fun. Because how is that different from what you're doing here now when you're yelling at flat earthers?
I did want to show one particular video, which I know that everyone says, show me the curve and all that sort of stuff, and how do you measure the ground? So a while ago, I went and did this test, and as you can see my dumpy level there is so low to the sand that I had to put on the top of the box, right? Because if I put it any lower, then you see how the stands are practically useless. They're bent out so far that they basically it'll just flat out fall into the sand. And so I only put the legs out to make sure that it wasn't going to wiggle when I bent down. And in this particular test, so I think it must be a photo of this one here. So I measured off the ground. I measured up to here. I set it to 50 centimeters and then figured out what its distance was down. So I tried to figure out, and so total 407 millimeters above the sea level. So as you could see there, I was risking getting a rusty tape in a rusty stand to be able to get this sort of thing. And you see how there's a cross here in the center.
Yeah, that's right. Yeah.
Right, there's a vertical one, and there's one across there. I think Ruyf even says that this top and bottom mark apparently might be a 1 degree variance.
Yeah.
So that's apparently 1 degree up and 1 degree down. Yeah. But you notice how this crosshair line is above this crest of this water. Now we know that the boat is behind the crest because we can see the shape of the boat below there. So we know that this is the horizon strike right here. And so I'm only 407 millimeters above the ground. Now you would say if we're looking at this boat, and I mean you can't quite see it just yet, but you would imagine if the bow is let's say it's about 6 meters, I must be at about the 3.5 meter height on the bow. Would you agree? Yeah. It's like more than halfway up the bow. And as you can see, that one only there was just to show that I'm still level. That hadn't changed. The boat comes in closer, and I mean this is the thing. Most people do this with cameras, and they don't do it with precision instruments like what I'm doing right now. And the boat comes in closer, and as you can see here, you've got like a silhouette right here. Sorry, no, it's not a silhouette. What talk about? It's got an inferior mirage, right? So the bottom of the L and the T and the O are severely warped by the mirage. So you would argue that maybe the actual true horizon, maybe it's like up here instead. Like if I was to say this distance down here looks like it's about, let's say it's a meter, I would say that the actual true horizon might be at the half meter mark, maybe. But as you can see, that boat continues to climb in height. to the point where, as you can see here, my strike line is on the bottom of the L. Now the crosshair is on the bottom of the L on this boat, and it was up higher on that L. It's almost, if you were to do a ratio on that, and there's the tell.
Yeah.
So my crosshairs must have been about up here on the L before. So from the third image to the fourth image, if that bottom leg of the L is about 1 meter in height, it's probably dropped probably dropped about a foot.
Yeah.
So there's no doubt that 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 you could see that the water is down below eye height.
Yeah.
And that means it's curving away.
Absolutely. So, absolutely right. I want to show you something. This is I found this. Now, hang on a second. I want to share this with you. Now, let me.
Did you want me to clear your other share? Because you've still got the other share.
Oh yes, yeah. Please, yeah. Please do that. I just want to present. I want to present something else. Okay, you got that.
How do I remove it?
Oh, maybe if I just replace it with something else, it'll do it.
Yeah.
Kick from studio, maybe.
Oh no, actually, it's I've got
that'll
it.
kick you.
Screen.
I can't do that.
No,
Yeah, you have to
gone now, is it? Is it gone
I'll
now?
go clear bank.
Okay. Share screen. And just let me do that, and you'll love this. Where is it? Is it a screen? Okay. I've got it. Oh, damn it! I've opened it up where is it? In search. It's not a tab. What do you share if you're not sharing a tab? It's a window, is it?
Is it image
window?
Or what is it?
There it is. Okay. Yeah, I got it. There we go. Look at this. Oh, but the children.
Oh, everyone died.
Can you see the?
I heard about this incident.
Everyone.
I heard that there was at least 1,800 people who died. It's tragic. Was it off the coast of Italy or something like that?
Yeah. Now, but the thing about it is, have a look at the stack.
Yeah, well,
it barely gets any smaller. Yeah. So what should that ship be doing? It should be getting smaller and smaller and smaller from all sides. It'd be good if we had That's what happens with perspective, isn't it?
Yep.
It'd be good if we knew 100% for sure that the zoom was the same, and that we could crop the stack for the image and be able to count the pixels across.
Oh, if we could find. I'm not au fait with how it is, but I'm sure that someone could find this actual the original video from which this came, and if someone can find the actual video from which this came, that would be definitive. Then you'd be able to use pixels to prove that. But I mean, this is a beautiful example.
I don't know.
Hang on, I'll stop sharing.
Ion too.
Yeah. Stop sharing. Okay.
Well, that's a good point there, Phil. You got a boat that goes over the horizon, and on a flat Earth, there wouldn't really be a horizon for miles away, wouldn't there?
No, there wouldn't be. No, you could see that horizon. That's clear as anything. That's that's beautiful.
I mean, me being able to see that smokestack on that boat is because we see too far.
Yeah.
Yeah. Let me.
This stuff bowls me over every fucking time, right? But whenever Alan or Shane says that our eyeballs is limited to a distance of 39.59 miles, I just go, our eyeballs receive light from wherever it comes from.
Yeah.
If it comes from a meter away, or if it comes from 10 kilometers away, or if it comes from 1,000 kilometers away, that light still will enter our eyeball, whether or not it has hit a brick wall on the way.
Don't I can go outside. It's night time. I can see the bloody stars. They're miles
That's
away.
it. The star. You can see the stars on the opposite side of the firmament, but there is no practical way. Is there any way for you to be able to get a man to stop and say, "Okay, you stay there very quietly. I'm going to quickly fly this way. When I get to 359, I'm going to see if there's a stop sign in front of your face to find out if the actual light has stopped." How do they measure that it's 359, or is it just appropriate that 3959 is actually relatively the radius of the Earth?
Yeah, look. So what they're doing is the snake oil salesman, which I'll call them that, who know
yes,
better.
Alan and Shane, snake oil salesman.
It seems logical to somebody who doesn't understand this, that if you take something further away, because they'll say, well, look, here's a candle. Could I see this candle from many, many miles away? You know, that's what they would say, right? Could I see this candle? So they say, well, the sun must be doing that, but the sun must be doing what the candle's doing. You know, I can't see the candle anymore. I can't resolve the candle, because that's really what the problem is. You can't resolve it. Okay, the candle's got too small to resolve. If the candle was the same height all the way, you'd see it, but you can't see the candle because you can't resolve the candle anymore. How can you say that about the sun though? And where did the sun go while the stars that are in the same direction are still there?
Yeah.
And this, presumably the stars that are in the same direction are on the opposites on the dome on the opposite side of the Earth, aren't they? You know, as far away as you could get.
Yes.
Yeah, on the dome, as far away you could get. Otherwise,
well, is it attached to the dome, or is it dangling off a chain?
I don't know, but are all these millions of stars just hanging around? I mean, if you go out in the country where there's no light, there's billions of stars.
Oh yeah.
Are they all hanging around in the atmosphere above, in the firmament, in that black area?
Yep.
You know, that black area where they pretending doesn't where space doesn't exist. You know.
Man, I once did a sketch about this. I'm gonna see if I can better search for it. Just give me a second. But you guys can continue talking. I think I've got to go and check my Flat Earth meme file.
Yeah. Whenever Flatzoid mentions my name, he talks about the black area, because that's my favorite thing, you know. So
yeah,
I said, well, you know, we see this thin blue area, because I asked him one day, I said, why is the sky blue? And he accurately said, it's because there's the air scatters the blue wavelengths. I said, okay, well, that's true. And he thought he was really clever because he answered it correctly. That's fine. Okay, so now you know why we've got this thin blue layer above the you know, that you can see from the vantage of a balloon. You can see this thin, because that's the atmosphere, right? That's where all the air is, right?
Yep.
Okay. Well, above it, why is it black then?
Yeah.
That's because there's no air up there. Why doesn't the air that's down there, all that blue stuff, go rising up and filling all that black area?
Man, you're going to hurt their brains doing this.
Yeah, you know,
it's going to hurt them.
This huge black area above this little thin blue area. Why isn't all that thin blue area just rush up there into that black area? I mean, what's stopping it? You know.
I found the meme which explains what keeps the moon and the sun in the sky.
Yeah.
If you're ready for this one again, I hope you guys don't get offended by this one.
Yeah, go for it. I'll go on.
So the sun and the moon are just dangling off God's nutsack.
God's.
I have to send that one to roast Danny's Telegram as well. I just thought that if he was up in space and something like that, it's just dangling from him. He's the only one who can control it.
Well, apparently he's got a sitting on a chair on top of the dome, looking down.
That's it.
That's what I gather. You know. Oh,
And who can
God.
buy a
How
stairway?
did this silliness start? You know,
I don't know.
actually, I got to give it. I got to give it to those snake oil salesmen. They really hit on a on a nerve there, didn't they? They thought there has to be some people dumb enough to think this, and they were right. There were.
Yeah. Right.
You know, and you could fleece them then because they're dumb.
But Phil, we've got a few of them in Australia, which I find insane.
Yeah, I know. It's hard to believe it. If you listen to that 24/7 show, there's quite a few of them there.
Really?
And I'm thinking,
My God.
well, at least 3 or 4 that I can think of, and you know, I mean, fair income. What? How do they do that? They especially us, you know, down here.
Yeah.
We have to be able to say, well, that's ridiculous, you know.
Yeah.
I mean, I'm over here I'm in Melbourne, and I'm thinking, well, I can see the sun. I go to Port Phillip, I look south, and I can see the sun heading sort of south. It's heading southwest, you know. I'm driving down the head-up display in the car. It's got a southwest on it, and it's heading straight into the sun, and it says southwest on the head-up display. Thinking, well, there you go, you know, and that's where the sun's going. It's definitely going southwest. Well, why aren't I turning? Why aren't I turning? And why isn't it at the back of my head? You know, you think you think if the Earth was flat, what would happen? You know, I mean, a normal person with a normal mind would think, all right, I would see the sun, a tiny little bright dot would come in all the way from the north, from the east, you know, north of east.
Yeah.
And it would come all the way and swing, and then spend the rest of the day going horizontally across my field of view, right? Not up in the air, horizontally. No. Okay. And then I'd watch it going to the west, and then heading back up north in a circle, going up north that way. That's what I'd see if
I wouldn't get any sleep.
You know, that's what you'd see, wouldn't you?
Yeah.
You know,
it's like when they said they heard him say quite a few times that nobody can actually go to Antarctica. And I think, hang on, my brother actually went and worked there for 6 months as an electrician, so I know the place exists.
yeah, exactly. Oh, they just, the whole thing's dumb. My wife's right. My wife's right. She's that they half of them have to be just. It's just a faith thing, you know.
Yeah.
They know it's wrong. It's just like I mean, let's face it. You know, because people say to me, well, if you how do the people, religious people that you know that you know, believe in you know, have a religion, they know how things work. So, well, you know, you have faith, you leave the signs at the door, you know, and then you walk in, and then after that it's all faith, you know. But you don't stand in there saying, while you're in there, saying anything about science, because then you've left it at the door. You know that no longer, once you walk past that door, it's all faith. It's all like, you know, stories, you know, it's just faith.
It's the human element. That's what it is.
The
human element.
The spirituality and all that. Yeah, exactly. Yeah. The science, you've left it at the door. You know that, you know. So that's how the scientists can walk into a church and believe in this and that and say, well, okay, well, that's fine. You can, because you know that it's a faith-based thing, you know, and you're not going to stand on the pulpit trying to make science sense of it scientifically, because you know that's impossible.
I know
you're not there for that.
No, they've got telescopes and stuff like that at the Vatican, so you know.
Yeah, they do. Yeah, and they, you know, they for them it was, you know, I mean, when in my youth I was in a seminary, you know, and they were huge into science. It was my uncle was actually a lecturer, and that's how I did my equivalent to VCE science, chemistry, when I was about 13 or 14 years old.
There you go.
You know, so, you know, so I did year 12 chemistry much earlier than anyone else. and that's because I was there, and there's not much a lot to do except did a lot of pacing and meditating and all the things that you do in a seminary. But they were big into science. It was so this idea that the church is anti-science is just nonsense. That's just total. That's bullshit. They're definitely not anti-science, but they're able to say this is science, this is faith. These totally different things, and we don't try to mix these up.
No.
Okay,
that's good. Because I have to admit, this last week, the biblical flat earthers have been trying to ram down the door quite hard, and I'm like, don't quote to me anything from a book that's 2,000 years old as being the most up to date proof, because that's just madness. Like they even, I think even Duffy's going to be talking about the what the definition of rakia is in Hebrew and stuff like that. Which, sure, you have to debate that, and you have to clear the air. But I just don't think that we should be taking any of this sort of stuff literally at all.
No,
cool stories.
Cool
look, stories. That's all it is.
Look, I'm not. I'm not against anybody who has who believes in that. I would love to believe all this. I'd love to think that all of this is true. I live my life hoping that it is. All right, because I've over here I've got the ashes of my son right over there. Wouldn't it be cool if I could get to see him? No, wouldn't it be cool if I could get to see him once again? How fantastic would it be if all of that was true? So I said, well, okay, let's make life just a little bit easier for me, having lost him, to say, well, mate, you never know. I'm not going to say no.
Yeah.
You never know. Down in myself, I'm a scientist, and I'm thinking, well, come on, Phil. But there's still that little bit of spark that I want to cling on to for my own health, for my own well-being, to say that wouldn't it be marvelous to see my son again? I hope like crazy it's true, right?
Yeah.
Okay. And it's a bit like buying one ticket in the lotto.
That's it.
And saying it's possible you could win it, because people do.
They do.
But the chance of you winning it is like an 89 to 1 million chance, right?
Yeah.
Okay. You would have to buy at least 80 million of those to make it possible.
Phil, have you ever heard about the movie The Invention of Lying?
No, tell me about it.
I have. I've seen
I would recommend it. It's a Ricky Gervais movie, and it's about a man who figured out how to start doing white lies and also to do dark lies too, right? But everyone was very literalist in the world, and people didn't really know what to believe. They just believed whatever was said, and so he saw his mother passing on, and he decided to start telling her a few lies, and he created religion. So this is right on the exact topic that we're talking about right now. If you have a bit of a watch, it's
I will.
It paints a picture. It paints a picture really, really in a good, fun way. It's hilarious as well
about how religion can happen.
How it just spawns into action.
Yeah, but it's not bad. It has its place, because in a way people say, well, it is the religion, and we'll make some rules. Don't kill people. Try not to steal their stuff.
If it comes out with good people, then I'm okay with it. If it makes you strap things to your chest, I'm not so happy about it.
Well, the Muslims go back a few centuries. They were really ahead of their time in science and stuff as well. So way before the Greeks were.
Yeah, but again, it's this being able to say, well, I'm not going to go in that place in the church there, just like that. I heard this pastor going in and saying that it was the sun was the devil. That it was the devil going.
Oh
around.
yes. Oh Jesus. That's crazy.
Crazy.
You know, I mean, that's just kind of irresponsible as well, you know, because there are people who will buy that, you know. And,
well, I know exactly what that is.
Thinking, well,
the question I had is like people sitting in the audience. Why didn't they arc up and say something about it?
No, but this is the thing. This is the thing. Is that particular pastor who was talking about the son being the devil?
Yeah.
Though that type of preaching in itself is, they try to entrap their pilgrims or whatever like that in a cycle of fear.
Yeah,
that's exactly what that is. So he's trying to make all those people into God-fearing Christians of a certain type, right? And to think that all these scary thing that's over there is going to kill you if you touch it. You know what I mean? It's kind of like, you know, when they electrocuted the elephant when electricity was new. They were saying, "Oh, don't touch electricity; it'll kill you like an elephant." That's what it was.
Yeah.
It's just a fear. It's implanting seeds of fear into people's minds.
Yeah, and that's it. And yeah, exactly. And well, I'm just thinking, you know, the thing about it is that I suppose from his point of view, you're thinking, well, what's his gain? And his gain is he's selling his message, isn't he?
Yes.
He's in a place where people will literally pay for that message, for what he's saying.
Yeah, exactly.
When they pay to go to these flat earth conferences, like, why would you pay for that?
Yeah.
Well, look, like someone said about it, you know, if you got to put on drinks and you've got to hire the hotel and the emporium and all this stuff, makes sense. Yeah. I've enjoyed the chat a heap tonight.
Yeah.
I'm understanding that obviously your wife is probably pretty pissed off at you right now.
Oh, she'd be asleep now. So
okay, well that's fine. It's certainly your time to go in there and tiptoe in and sneak in and go to sleep, because I'm sure we all do. But our English counterparts over there are probably like raring for us to go for another hour. But I don't think that's fair on anyone on this chat.
And thank you so much, Phil.
I hope anybody watch. If the people are in a chat or something like that, I'm sorry I haven't answered it. If you've asked me questions, I haven't.
Is there any particular?
I haven't even been watching it. Yeah.
I don't think there's been any particular questions. There's been a few statements talking about like there was earlier statements talking about you know, gravity and all and other things, but I think in a lot of cases, most of the chats are all sort of you know, backing up what we were talking about. There was a bit of chat about time in Wales and stuff like that, so a few laughs. So there was no specific questions.
Okay, all right, never mind. All right, well, I think I'm going to get going.
Yeah,
so
it is time
that's so much, Phil. It's been
let's catch up again. It was good.
Yeah, we'll have to do it again, and this time I think what Mum Bakes Cakes. Maybe I saw someone saying huge ass. He mentioned huge ass. Maybe I should like try to throw a line his way and try to get him involved and stuff like that. Get more of these Aussies back on board.
Huge ass is worth his weight in gold, which apparently is going to be a lot.
Yeah, a lot of gold.
That picture of him,
okay.
That picture of him in Antarctica, that was hilarious.
No, I love talking to Hugh. It's fun. Great deal of fun. Yeah, he's a great Aussie.
But most Aussies are, Phil. But most of us are.
Yeah, I'll have to go. We'll have to get critical thinking here, too.
Okay, all right. Great talking to you guys.
All
right, well,
yeah.
I want to. Yeah, we can talk about that experiment was really, really great. Some of these should be documented because I mean they'd make good stuff for schools, you know, and things like that. Especially it's critical things experiment. The one that they did in the snow, that's fantastic, you know, and showing that to kids and stuff like that. There's a lot of good little ones that can be packaged properly. And then used as a teaching tool.
Yeah, definitely. Any final thoughts?
Cool.
Well, my final thoughts are this: I want to try and hopefully forget about the flat earthers eventually. Although I must admit, I've come across, like you guys and the people on Toon's show and all of that. So it's, you have a bit of fun, but really, if they start influencing kids, I really want to see the end of it.
Yeah.
Yeah.
There's no doubt that it's about the friends you make along the way, and we learn little bits along the way as well. I mean, I know, Professor Phil, you pretty much know everything these days, but I mean, all of us do. We all do collectively learn a little bit more, each time.
No, we do. No, we need everybody. So, I mean, Ruhif's the mathematician. He is invaluable for doing the calculations, stuff that takes a lot of time to do.
Yeah,
and and dedication. I look at that and I think, you know what? I'm just too lazy. I'm going to give that to a student to do. I'm not going to do that.
I like to do all the sketches and the drawings.
Myself,
I'll do the catering.
When students come to me and they say, "Oh, can you work this out yourself?" I said, "No, you work it out. You work it out, and you show it to me. You show me what you did, and then I'll go through it and see if I think you're right."
There you go.
So yeah, no. No. We need the Ruhifs around. So, all right.
That's it.
Okay.
All right. Good night, everyone.
Good night.
All right.
I'll start shutting it down.
Okay then. All right.
See ya.
Bye-bye. Okay. Cheers.